Have you ever stopped to think about what really happens when a supersonic plane cuts through the sky at speeds that defy our comprehension? We're talking about machines that travel faster than the speed of sound, exceeding an incredible 1,235 kilometers per hour, leaving behind a sonic boom that makes windows tremble and hearts race. But what few people know is that behind this impressive speed lies a fascinating combination of extreme physics, millimeter-precise engineering, and technological secrets that have been kept under lock and key for decades, secrets that have completely transformed our understanding of flight and continue to evolve to this day in ways you can't even imagine. The history of supersonic aircraft doesn't simply begin with the desire to fly fast, but rather with an urgent military need during the Cold War, when nations fiercely competed to dominate the skies and establish technological superiority. It was precisely in this context of tension and accelerated innovation that discoveries emerged that forever changed aviation. The first fundamental secret lies in how these aircraft are designed, because unlike the commercial aircraft you see every day at airports, supersonic jets have an absolutely unique design that seems to have come straight out of a science fiction movie, with extremely streamlined fuselages, delta-shaped wings or aggressively angled wings, and pointed, needle-like noses that literally cut through the air in a way that minimizes drag to the extreme. When we talk about supersonic speed, we're dealing with something called the Mach number, a measure that compares the speed of an object to the speed of sound in air. And here's something interesting that most people are completely unaware of. The speed of sound is not constant. It varies depending on temperature, altitude, and air density. This means that flying at Mach 2 at sea level is completely different from flying at Mach 2 at stratospheric altitudes, where the air is ting and icy. The legendary Concorde, which carried passengers across the Atlantic for decades, flew at Mach 2.04, meaning it could cross from London to New York in just 3.5 hours, half the time of a conventional flight, and passengers could literally see the curvature of the Earth out the window while traveling on the edge of space at an altitude of 60,000 feet. But the real secret behind this incredible speed lies not only in the aerodynamic design, but also in the revolutionary engines that power these machines. Engines that need to function completely differently depending on the speed at which the aircraft is flying, undergoing internal transformations that adjust the airflow automatically and with extreme precision. Conventional turbojet engines simply cannot handle the extreme conditions of supersonic flight, where the air entering the turbines is violently compressed by the speed, creating temperatures so high that they could melt ordinary metal in a matter of seconds. And that is why engineers developed turbojet engines with afterburners, which inject additional fuel directly into the exhaust stream to generate a massive extra thrust. Can you imagine how much fuel these machines consume? The Concorde burned approximately 25,000 liters of fuel just to cross the Atlantic, a consumption so absurd that it made the operation economically challenging, but absolutely necessary to maintain those stratospheric speeds that defied the laws of traditional physics. And here comes another fascinating secret that few know. When an airplane exceeds the speed of sound, it encounters something called a sonic barrier, a phenomenon where shock waves form around the aircraft, creating an invisible wall of resistance that needs to be literally pierced. And it is at this exact moment that the famous supersonic boom occurs, that deafening noise that is actually the sound of multiple shock waves propagating through the air like a continuous explosion that follows the plane throughout its trajectory. The pilots who first broke the sound barrier reported terrifying experiences where the aircraft would begin to shake violently, the controls would become unstable, and there was a genuine fear that the structure would simply fall apart in mid-air. But Chuck Yeager, the legendary American test pilot, on October 14, 1947, aboard the Bell X-1, proved that it was possible to survive and control an aircraft at supersonic speeds, opening the doors to a new era of aviation. From that historic moment, engineers around the world began to unravel the mysteries of supersonic flight, discovering that the shape of the wings needed to be completely rethought, that the construction materials needed to withstand unimaginable stresses and temperatures, and that entirely new control systems needed to be developed to maintain stability when extreme aerodynamic forces tried to tear the plane to pieces. One of the most impressive and least known aspects is how These aircraft handle the heat generated by friction with the air at supersonic speeds. When you're flying at more than twice the speed of sound, the friction with air molecules generates so much heat that the fuselage can reach temperatures exceeding 100 degrees Celsius. In the case of the SR-71 Blackbird, the fastest spy plane ever built, which flew at Mach 3.3, the fuselage reached 300 degrees Celsius, temperature high enough to make you drop a steak on the wing and it would cook during flight. Because of this extreme heating, the Blackbird was built with a special titanium alloy and needed to be refueled in mid-flight because fuel leaked from the tanks when the plane was stationary on the ground. Since the parts only fit together perfectly when expanded by the heat of supersonic flight in engineering detail, as bizarre as it is ingenious, demonstrating the level of sophistication required to master these speeds. The pilots of these planes also needed very specialized training and wore pressurized suits similar to those of astronauts, because flying at stratospheric altitudes means being in an environment where the atmospheric pressure is so low that human blood would literally boil if there were a sudden deep, and the G-forces experienced during high-speed maneuvers could easily cause pilot to faint if he was not properly prepared and protected. But why don't we see more commercial supersonic aircraft in the skies today if the technology has existed for decades? The answer involves a complex combination of economic, environmental, and political factors that make operating these aircraft extremely challenging in the modern world. Starting with the brutal fuel consumption we mentioned, moving on to restrictions on supersonic booms over inhabited areas that force aircraft to fly at subsonic speeds over land, and finally arriving at environmental concerns about emissions at high altitudes that affect the ozone layer in ways not yet fully understood. The Concorde was retired in 2003 after decades of glorious operation, leaving the world without any civil supersonic transport options. But that doesn't mean the story ended there. Quite the contrary, because at this very moment there are several companies and projects around the world working to bring back the supersonic era with completely new technologies that promise to solve all the problems that doomed the first generation. Boom Supersonic, for example, is developing the Overture, a supersonic jet that promises to fly at Mach 1.7, carting up 280 passengers with far superior fuel efficiency using modern engines and advanced composite materials. And NASA is testing the X-59, an experimental aircraft specifically designed to eliminate the supersonic boom through a revolutionary design that transforms the shockwave into a smooth sound similar to distant thunder, a technology that, if successful, could completely revolutionize regulations and finally make supersonic flight over land viable. The secrets of supersonic speed also involve highly advanced computational aerodynamics that simply didn't exist at the time of the Concorde, with simulations that can predict with millimeter precision how the air will behave around each curve of the fuselage at different speeds and altitudes, allowing optimizations that were previously impossible and resulting in designs that are simultaneously more efficient, quieter, and more economical. Materials have also evolved dramatically, with carbon fibers, next generation, and exotic metal alloys that are lighter and stronger than anything available in the last century, reducing structural weight and allowing more space to be dedicated to passengers and payload instead of fuel. And we cannot forget the advances in propulsion, with engines that incorporate hybrid technologies, integrated noise reduction systems, and the ability to operate with sustainable aviation fuels that can drastically reduce the environmental impact of these aircraft. The future of supersonic aircraft may also include even more radical concepts, such as hypersonic planes that would fly at Mach 5 or more, reducing travel time between continents to mere hours, and potentially even making suborbital flights possible, where the aircraft would briefly leave the atmosphere before re-entering on the other side of the planet. Concept that seems like science fiction, but is being actively researched by space agencies and private companies that see it as the future of high-speed intercontinental transport. The physics behind all of this is absolutely fascinating when you really stop to understand it, because we're not just talking about pushing more air back to go faster, we're talking about managing complex shock waves, controlling turbulent boundary layers, optimizing compression and expansion ratios in engines where air enters subsonically and exits supersonically, dealing with aeroelastic instabilities, where the structure can resonate and coordinating control systems that need to respond in milliseconds to keep the aircraft stable in conditions that would change instantly if you moved the control stick just a few millimeters. And then there's the issue of the windows. Because did you know that the Concorde's windows were extremely small precisely because windows that were too large would become dangerous structural weak points under the stresses and temperatures of supersonic flight, and that they were made of multiple layers of special glass that could expand and contract without cracking. Every detail in a supersonic aircraft is carefully considered and redesigned multiple times, taking into account conditions that simply don't exist in conventional flights, from hydraulic systems that need to operate with special fluids to onboard computers that process thousands of adjustments per second to keep everything running perfectly. So if you think you already understand everything about airplanes, think again, because the supersonic world is a completely different universe, where normal rules simply no longer apply, and where human engineering needs to be pushed to the absolute limit to make the impossible a reality. If this topic has sparked your curiosity, and you want to continue exploring the most impressive secrets of aviation and the technology shaping our future, don't forget to like this video, subscribe to the channel, and activate the bell, so you don't miss any exclusive content we prepare. And tell me in the comments what speed you think future airplanes will reach, and if you would have the courage to fly in a supersonic jet knowing everything that happens behind that incredible experience. Click now on the video that's appearing on your screen to continue discovering facts that will completely change the way you see the world around you.